Hello everyone, a very warm welcome to the teaching show. I am Dr. Poonam Nigam, and in this video again we will take one more problem on recycle. So I am taking several problems on recycle. Each video has a different theme to it, and I am trying to teach you some specific concepts using one example every time. Okay, so this in this video I am taking an example of recycle problem with process stream which is given as a basis. Till now whatever problems we had seen, they had either you were given the feed flow rate or something about this, or your product stream which was coming out. Okay, so that's why you could start by taking the overall balance. Now in this case there is a slight difference. You don't know anything about what is coming in or what is going out. Okay, what you have been given is that just the product stream which is coming out from the reactor, its molar flow rate is 350 moles per minute, and further its composition is given, but just look carefully that what is happening is that you have its molar composition. Instead of giving the molar composition, they are giving you composition in weight percent. Okay, so you have to be very careful while doing any problem, whether you have like everything in mole and mole percent, or they have taken the mixed units. So this is given. Now what else is given? Okay, I will explain the problem to you. This problem is taken from Felder. It is unsolved 4.57. The reaction which is taking place is carbon monoxide reacts with hydrogen to give you methanol. The fresh feed which is coming in contains only carbon monoxide and hydrogen, and then it combines with the recycled stream which contains 0.4% of methanol. Okay, so now this recycled stream, it combines with your fresh feed, and the combined feed goes to the reactor. So all three components are there. Okay, and in the exit also three components are there. Now it goes to the separator, from where methanol is most of the methanol is removed as product, but a small part it still stays. Okay, it's not separated completely, so it goes back into the recycle stream, but hydrogen and carbon monoxide, they are completely separated. So we have methanol also, like a portion or fraction of the product which is being recycled back. Okay, so you have been given only two information, one that is 350 moles per minute and this composition, and second thing which is given is that the mole fraction of methanol in the recycle stream. Okay, now you have to solve this problem. So before starting to solve this problem, what I will do is, first I will make all the units uniform. Okay, so I will first go and convert this weight percent into mole percent, or better it will be that I convert it into molar flow rates. Okay, so I have already taught this in lecture 1 or 2, I don't remember, you can go and check. Okay, I will put the link. So while converting, what you have to do is, first of all, forget that you have 350 moles per minute. Just assume that you have 100 grams of this product stream which is going out. Okay, so I am taking 100 grams of reactor product. If I have 100 grams of reactor product, then it contains hydrogen 10.6 grams, carbon monoxide 64 grams, and methanol which is 25.4 grams. Okay, just on my basis of 100 gram of reactor product. Now I will convert it into moles by dividing with their molecular weights. So 10.6 divided by 2, 64 divided by, what it will be, 16 plus 12, so 28. So 64 divided by 28, I get this number. Then methanol, its molecular weight is 32. So I will divide 25.4 by this number 32, and I get this. Okay, so these are my, if I have chosen a basis of 100 grams of reactor product, then I have these many moles. The total number of moles I have calculated. Now next step is to calculate the mole fraction. So I will calculate 5.3 divided by the total number of moles, that gives me 63.26% of hydrogen. Similarly, this divided by this gives you mole percentage of carbon monoxide, and so on. Okay. So now I have mole fractions. If I want to calculate my molar flow rates N1, N2, N3, what I have to do, because I know my molar flow rate, total molar flow rate is 350 and the mole fraction is of hydrogen is 63.26. So I will multiply 350 by 0.6326 and then I get this number. Okay, so I have converted my mole percentages or mole fractions into the molar flow rates. So I have for hydrogen, now I will update my this thing, flow sheet. Okay, and then we will start solving the problem. So my N1, that is equal to 221.41. Then my N2 is it is 95.445 and my N3 is 33.145, and all these are in moles per minute. Okay, just remember the units. Fine. So I have calculated till now, I have converted all the mole fractions into, I have converted all the weight fractions into mole fractions. Now let's start the problem. Okay, I told you, let's try and take my overall degree of freedom. I have 3 unknowns, okay, plus 1, there is one reaction. So 4 unknowns. If I am using my molecular species balance, okay, then in that case also I have only 3 independent molecular species balance which I can write. There is no other process specification, so degree of freedom is 1. Okay, you can try with any other methods, your degree of freedom will not come out to be 0. So I cannot start with the overall balance. So now what I will do is that, okay, let me check on the reactor now. Okay, because I know all these effluent stream composition. So you might think, okay, let's try over here because there is a reactor which is involved in this. Let's go directly and take atomic species balance. Okay, if I take atomic species balance, how many variables do I have? 1, 2 and 3. So I have 3 variables. Okay, reaction we are not going to count because this is atomic species balance. Then how many independent atomic species balance I can write? See, there are 3 unknowns and then CO, H2 and CH3OH. You observe that carbon and oxygen, they always appear in the same ratio. So I have either, I can use either carbon or I can use oxygen balance because they are not independent of each other. So I have only 2 independent atomic balances, that is either carbon or oxygen plus hydrogen. So I have 2 independent balances. I don't have any other process specification. So my degree of freedom is 1. I cannot solve on the reactor. Let's go and check on the separator. I told you in the last video that separator, no reaction is taking place. So always take your molecular species balance. So let's do that. How many unknowns I have? NP, NR and XH. So I have 3 unknowns, and how many molecular species balance I can write? I can write 1 on each, that is CO, H2 and CH3OH. So I have 3 balances, I have 3 unknowns, so I can start my calculations from the separator. Okay, so I am going to start doing that. Let's do it quickly. Okay, so let's write first hydrogen balance. Okay, if you get confused, I will write what it means. This is hydrogen, this is CO and this is methanol. Okay, so let's write hydrogen balance. So my N1 should be equal to XH times NR. Okay, I just know N1, so I'm going to write it as 221.41. There are 2 unknowns, I cannot solve this equation. Let's go and write CO balance. What it gives me is that N2 is equal to 95.445, okay, and that should be equal to CO. It's not coming out in that stream, it is only coming out over here. So I have NR times 1 minus 0.004 is 0.996. So I am going to write 0.996 minus XH. Okay. Now from here where I can go, I will just do one thing. Okay, now I just open this bracket. Okay, so I get 0.996 Nr minus XH times Nr. Okay, now XH times Nr, I know that it is 221.41. So I am going to write over here 221.41. Okay, so this is 221.41. Now I have an equation which is only in one unknown, that is Nr. Okay, so I will use this equation to find out what is the value of this flow rate of this recycle stream. Now this flow rate, it comes out to be 318.12 moles per minute. Okay, now I will keep on updating my flow chart. Now I can use this over here and find out what will be XH. So the mole fraction of hydrogen in the recycle stream, if I use that, it comes out to 0.696. Okay, so I will update it 0.696. If I know this is 0.696, this is 0.004, so I should be able to calculate this one because the addition should come out to be 0. So this comes out to be 0.3. Okay, the remaining thing which is left is my product flow rate. So I am going to take methanol balance. Now methanol balance will be what? N3. That should be equal to my NP plus 0.004 times my NR. Okay, I know what is N3, I know what is NR, so I will calculate my product flow rate, and this comes out to be 31.87 moles per minute. Okay, so I have this one also, 31.87 moles per minute. So I have solved now my separator. Okay, now I will go and check where my degree of freedom, now it has reduced to 0. Okay, so let's see, on the reactor still I cannot solve it. Okay, so let me go and check on my mixing point. Okay, so on mixing point, how many unknowns I have? Okay, again I have on mixing point 1, 2, 3, 4, 5, nowhere to go. Okay, so on reactor also my degree of freedom is not 0. On my mixing point it is not 0. So now because I know my product stream, let's try overall balance. Okay, so if I take the entire system, then okay, because there is a reactor over there, let's try atomic species balance. Okay, so again you will see that C and O, they appear in the same ratio everywhere. So I have only 2 independent atomic balances, that is carbon, either carbon or oxygen, and hydrogen. So I have 2 independent atomic species balance and I have 2 unknowns. Okay, so now I can take my this thing, okay, why am I erasing it? So I can take my balance on the overall system. Let's take it and find out what will be the values. Okay, so let's first take either carbon or oxygen balance. How much is going in carbon or oxygen? That is N4, and that should be equal to how much is coming out? 31.87 moles per minute. So directly you got the value of your N4. How much is N5 which is going in, or hydrogen which is going in? 2 times N5, and that should be equal to 4 times Np, or 4 times 31.87, or you have N5 which is equal to 2 times 31.87, or this is 63.74 moles. Okay, so I have calculated now N4 and N5. N4 is 31.87 and this is 63.7 moles per minute. Fine. Now I can go and solve my mixing point. Okay, because now I know two things. This will be simply a molecular species balance, because I told you no reaction is taking place over here, so you can go and take molecular species balance. Quickly take molecular species balance and solve this problem. Okay, so let's take molecular species balance. There are three unknowns and three independent molecular species balance I can take. So I'm going to find out. First of all, let's take CO balance. Okay, so how much it will be? 31.87 plus 0.3 into 318.12. Okay, that is going in, and that should be equal to what is coming out, that is N6. Solve for this. Then we will take hydrogen balance. How much is hydrogen going in? It is 63.7 plus 0.696 into your flow rate 318.12, and that should be equal to your N7. Then you take your methanol balance. Nothing is coming in from the fresh feed, only the recycle. So I have 0.004 times your NR, that is equal to your N8. So find these values, and I am going to update it in the flowchart. So what values do I get? I am going to write now. Let's see. So N6 is 127.3. Then I have N7 is 285.15, and my N8 is 1.272. Okay, so now I have the composition and all the flow rates I have calculated. So now I have a balanced flow chart. Okay, now whatever they have asked, you can calculate from here. The fresh feed which is going in, the ratio, what is the product stream, what is the recycle ratio, everything you can calculate from here. When I had taken my balance on the overall I had used my atomic species balance. I could have also solved this using my extent of reaction. Okay, now let's first check what is the overall conversion and the single pass conversion. Okay, so what is my overall conversion? What is going in? So reacted upon fed. How much is reacted? CO, nothing is coming out, everything is reacting. So your overall conversion is 100%. What is your single pass conversion? Let's find that. Okay, single pass conversion is how much is converting, that is reacting, that will be equal to, first of all you will have to find out which one is the limiting reactant out of this. So your stoichiometric ratio of hydrogen to CO is 2:1. Now if you see over here, 285 divided by 127, it is a number which is bigger than 2. That means hydrogen is in excess and your carbon monoxide is limiting. So I will base my conversion on the CO. Okay, so let's see how much has reacted. That will be equal to 127.3 minus 95.445, and that divided by what is fed and multiplied by 100. So you get 25%. So single pass conversion is basically 25%, but your overall conversion is 100%. Let's see, if I ask you what is the extent of reaction, okay, then you may be confused whether you want to base your extent of reaction calculations over here or on the entire system. Okay, so I will tell you, it doesn't matter whether you base your calculations on the reactor or on the overall system. Whatever extent of reaction you are calculating, it remains the same. Let's see, first let's calculate, okay, and then I will give you an explanation. Okay, so my let's say extent of reaction by using these compositions. Let's take the simplest one. What is the amount of methanol which is formed? Okay, so my final composition of this thing N3, that should be equal to what? My N0, that is N8 plus zeta, and this is plus 1. Okay, so plus zeta. So zeta will be equal to N3 minus N8, and it will come out to be, what is N3? 33.145 minus 1.272, and that comes out to be 31.87. Let's calculate zeta based on my overall values. Then let's do it for this thing again, methanol. So I have how much methanol is going in the fresh feed? Nothing. What is coming out is 31.87. So my NP, that should be equal to 0 plus zeta. What is my NP? That is 31.87. That is equal to zeta. So what you observe over here is that however you may calculate, either you use your feed flow rates on the reactor or you use it on the overall system. Whatever you do, your extent of reaction always comes out to be the same. So don't get confused that if you have like single pass conversion is 25% and your overall conversion is 100%, you might think that if you base your extent of reaction calculation on these product and feed stream, then you will get a higher zeta. No, it doesn't happen like this. The extent of reaction, basically it is an information about the reaction itself. Okay, so how much reaction is taking place within this reactor, that is not going to change. Fine. So that's why it is a function only of the reaction kinetics and thermodynamics. So it is fixed. How many number of moles reacting in this are fixed, whether you recycle it or not. But your conversion changes. Okay, but your extent of reaction remains the same. So this becomes very handy when you are solving recycle problems, because let's say I have calculated my zeta based on this and this. Okay, then that zeta I can use over here itself. Okay, so when I take balance on the reactor, I know one of the unknowns, that is my extent of reaction, and I can use it over here. So that we will see again in next video. I will take another problem on recycle and use this concept. Okay, so thanks a lot for watching and thank you very much. If you like my video, please don't forget to subscribe to my channel and hit the like button. Thank you so much.